Okay, hi everyone, welcome back to this video series on data centers. Routing basics. Once you create an internetwork by connecting your networks to a router, you'll need to learn to configure logical network addresses such as an IP address to all hosts on the internetwork so that they can communicate across that internetwork. The term routing is used for taking a packet from one device and sending it through the network to another device on a different network. Routers don't really care about hosts, they only care about networks and the best path to each network. The logical network address of the destination host is used to get packets to a network through a routed network, and then the hardware address of the host is used to deliver the packet from a router to the correct destination host. If your network has no routers, then it should be apparent that you are not routing. Routers route traffic to all networks in your internetwork. To be able to route packets, a router must know at a minimum the following: destination address, neighbor routers from which it can learn about remote networks, possible routes to all remote networks, the best route to each remote network, how to maintain and verify routing information. The routers learn about remote networks from neighbor routers or from an administrator. The router then builds a routing table that describes how to find the remote networks. If a network is directly connected, then the router already knows how to get to it. If a network isn't directly connected to the router must go one of two ways to learn how to get to the remote network: static routing, meaning that someone must hand type all network locations into the routing table, or something called dynamic routing. In dynamic routing, a protocol on one router communicates with the same protocol running on neighbor routers. The routers then update each other about all the networks they know about and place this information in the routing table. If a change occurs in the network, the dynamic routing protocols automatically inform all routers about the event. If static routing is used, the administrator is responsible for updating all changes by hand into all routers. Typically in a large network, a combination of both dynamic and static routing is used. Before we jump into the IP routing process, let's take a look at a very simple example that demonstrates how our router uses the routing table to route packets out of an interface. We'll be going into a more detailed study of the process in the next section, but what I'm showing now is called the longest match rule, which means that IP will look through a routing table for the longest match compared to the destination address of a packet. Let's take a look. Figure 9.1 shows a simple network. Lab A has 4 LAN interfaces. Looking at figure 9.1, can you see which interface you will use to forward an IP datagram to a host with a destination IP address of 10.10.10.30? By using the command show IP route on an iOS router, we can see the routing table map of the network that Lab A uses to make forwarding decisions. Lab A SH IP route output CUT. Gateway of last resort is not set. 10.0.0.0/8 is variably subnetting 3 subnets, 3 masks. 10.0.0.0/8 is directly connected fast Ethernet 0/3. 10.10.0.0/16 is directly connected fast Ethernet 0/2. 10.10.10.0/24 is directly connected fast Ethernet 0/1. 0.0.0.0/0 is directly connected fast Ethernet 0/0. The S in the routing table output means that the networks are listed are statically configured or administratively configured, and until we add our routing protocol, something like RIP or EIGRP, to the routers in our internetwork. By default, we'd have only directly connected networks in our routing table, but in this example 4 static routes have been configured. So let's go back to the original question. By looking at the figure and the output of the routing table, you can tell what IP will do with the received packet data destination IP address of 10.10.10.30 ? Well, the answer is that the router will packet switch the packet to interface fast Ethernet 0/1, and this interface will frame the packet and then send it out on the network segment. To reiterate on the longest match rule, IP would look for the destination address 10.10.10.30, and in this example the packet would match 4 entries in the output. But IP would use the longest match, which means both IP address and the mask and /24F0/1 is the longest match. Because we can, let's compare the iOS routing table output to a Nexus 7000 output with a similar basic configuration. First, we'll configure the 10, 100, 1000 Ethernet card in slot 3 of the Nexus 7000 with 4 connections, and then we'll display the routing table and discuss it. Nexus 7000 config, enter configuration commands 1 per line, end with CNTLZ. Nexus 7000 config int E3/1 Nexus 7000 config if no switch port. Nexus 7000 config if IP address 10.10.10.1 255.255.255.252. Nexus 7000 config if no shut. Nexus 7000 config if int E3/2. Nexus 7000 config if no switch port. Nexus 7000 config if IP address 10.10.10 17.255.255.255.240. Nexus 7000 config if no shut. Nexus 7000 config if int E3/3. Nexus 7000 config if no switch port. Nexus 7000 config if IP address 10.10.10.66 Nexus 7000 config if no shut. Nexus 7000 config if int E3/4. Nexus 7000 config if no switch port. Nexus 7000 config if IP address 10.10.1.1 255.255.255.0. Nexus 7000 config if no shut. Nexus 7000 config if SHIP route. IP route table for VRF default denotes best UCAST next hop, denotes best MCAST next hop. XY denotes preference / metric. 10.10.1.0/24 U best MBST 10 via 10.10.1.1 ETH 3/4 0/0:00:21 direct. 10.10.1.1/32 U best MBest 1/0 attached via 10.10.1.1 ETH 3/4 0/0:00:21 local. 10.10.10.0/30 U best MBest 1/0 attached via 10.10.10.1 ETH 3/1/0/000 :00:16 direct, 10.10.10.1/32 ubest/mbest1 /0 attached via 10.10.10.1 ETH31 0/000:00:16 local, 10.10.10.16/28 ubest/mbest 1/0 attached via 10.10.10.17 ETH30/2 0/000:04:55 direct, 10.10.10.17/32 ubest/mbest 1/0 attached via 10.10.10.17 ETH3/2 0/000:04:55 local, 10.10.10.64/26 ubest/mbest 1/0 attached via 10.10.10.66 ETH3/3 0/000:00:15 direct, 10.10.10.66/32 ubest/mbest 1/0 attached via 10.10.10.66 ETH3 4/3 0/00:0015 local. Now that's a different routing table. If you're used to iOS, which most of us are, this is a much different output. However, once you spend some time studying this, you'll get the hang of it. Basically, it's the same thing. Routing is routing, but it's just displayed differently, and one destination network uses 4 lines in the table. The easier to understand if I try and display the output in 2 lines instead of 4 using E3/3 interface as an example. 10.10.10.64/26 ubest /mbest 1/0 attached via 10.10.10.66 ETH3 0/3 0/0:00:15 direct, 10.10.10.66 /32 ubest/mbest 10/1 attached via 10.10.10.66 ETH3 /3 0/00:00:15 local. First, you see the attached connected subnet 10.10.10.10.64/26 via the exit IP address exit interface, pretty much the same as an iOS output. However, what they have listed next is the output, which is not in an iOS output, is the actual interface IP address listed as local in the routing table. When this IP address is the destination IP address of a packet, IP will then parse the routing table and see that this is a locally attached IP address and not forwarded out to the interface E3/3 in this example. One last thing, this is also new. The ubest/mbest 1/0 is the unicast next hop and multicast next hop for the listed network. Notice the 1/0 attached via. This is telling us that there is a single unicast address considered the best next hop. If there were 2 routes that were equal to the remote network destination address, then the output will display 2 1/0. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.